In this video, we're going to finish off this topic of exponentials and logarithms, and we're going to look at logarithmic functions with missing constants. So in previous examples, we've been given the equations of logarithmic functions, but sometimes we're given information about a logarithmic function without actually knowing the function explicitly. And when this happens, we can actually use the information given to determine the specific equation of the function. Now, you may remember that we did a very similar exercise for exponential functions. So maybe you'll remember from there that we substitute in any points that were given and we're able to work out the missing constants. So let's have a look at the first example. We are told that part of the graph of y equals log to the base a of x is shown, and we're asked to find a. Now, you may remember from 2 lessons ago from looking at the graphs of logarithmic functions that if you have a graph with equation of the form y equals log to the base a of x, which we have here, that will pass through the points 1, 0 and a, 1. And in this graph shown, we've got 1, 0 and 5, 1. So you might be able to see by inspection that a is equal to 5. But if you can't see that straight away, that's absolutely fine. We can use the algebra here and we can work out what a is, so that's not a problem. So we've been given the point 5, 1, which is made up of an x ordinate and a y ordinate. And you can see that the equation we have been given also has an x and it has a y as well. So we can substitute in here. We're going to have 1 equals log to the base a of 5, and then expressing this in exponential form will give us a to the 1 equals 5. We know that a to the 1 is just a, so a is 5, and that is our final answer here. So just now would be a good time to pause the video and copy this into your notes. Now, let's have a look at example 2. So part of the graph of y equals log to the base m of x plus k is shown, and we've to find k and m. So you can see here we've got a graph that has obviously been transformed because it's not passing through the point 1, 0 as the basic log graph normally does. So it's obviously moved here, it's moved to the left, and we've got the points -4, 0 and 5, 1. So again, like I said, you might know that it normally passes through the point 1, 0. You can see it's moved 5 units to the left. So you might know by inspection that k will be equal to 5. But like I said, the last time we have the algebra there as a sort of backup if you're not able to just look at the graph and work it out. So we've been given the 2 points, like I said. We've got -4, 0 and we've got 5, 1. And those are both made up of an x ordinate and a y ordinate, as you well know by now. Our equation has an x and a y in it. So we are able to substitute in. So we've got y equals log to the base m of x plus k, which is 0 equals log to the base m of -4 plus k. Now, expressing that in exponential form, we will have m to the 0 is equal to -4 plus k. But we know, folks, that any variable or any number to the power 0 gives us 1. So 1 is equal to -4 plus k. Adding 4 to both sides gives us k equal to 5. And obviously I'd said that earlier, if you were able to see it by inspection, that was fine. Now, we now have an equation of this form. Y equals log to the base m of x plus 5. That was previously k. And we've got this point that we've not used yet, 5, 1. So we can substitute that in. And we'll have 1 equals log to the base m of 5 plus 5. Which obviously we can evaluate the 5 plus 5, which is 10. We've got 1 equals log to the base m of 10. Expressing that in exponential form gives us m to the power 1 equals 10. We know m to the power 1 is just m, so m is 10. So just now would be a good time to pause the video before the screen goes blank and copy this into your notes before doing the assigned exercise for today.